All right, I'm sorry for the wait. Welcome everyone to another Quantum Matter seminar.
Let's see.
I use your
All right. Should we start from the beginning?
You wanna mute, Adrian?
No, but
that's me.
Yeah. All right. I guess we have to start a couple slides back, maybe, or from here. Anyway, for those that haven't heard my introduction, I give you Chris White from the University of Maryland, and I'm sorry for the mishap.
Yeah, okay. So we all say we want to understand things like quark gluon plasmas. So what happens when you run a couple of gold nuclei together, or what happens in a cuprate? I will be very upfront and say, first of all, that this talk is about one-dimensional spin models, right? And it's about one-dimensional spin models at infinite temperature, not at finite temperature. Second of all, like I'm not super pessimistic. I think maybe given time and effort, we can do, let's say, 2D Fermi Hubbard at high temperature on a classical computer. I do not think we're ever going to do QCD on a classical computer. But the goal here is to understand the generic physics that gets you from, again, unitary microscopic dynamics to long wavelength effective dynamics. And I want to be very explicit that I'm talking really this talk about infinite temperature, which I know is sort of the opposite limit from where Adrian, you and your people tend to spend a lot of time, like, ground state excitations over the ground state. So it's a different world. The two things I'm thinking about are first, long time tails. These are a phenomenon where nonlinear corrections to diffusion, so purely classical corrections, give different relaxation of currents. And second, some short wavelength oscillatory behavior. So reasons you might care about long time tails, I am not super excited about them. One important one reason you might care about them is that they control how hard you have to work to get the genuine infinite time limit of your dynamics. Like if you want to extract the diffusion coefficient, you care if you're approaching that like an exponential or like a power of one. So the short wavelength oscillations, I think are, oh, sorry, I'm trying to hide this. Yeah, I think those are more interesting. I think, first of all, that they're this sort of finite wavelength, finite time behavior it's a more detailed probe of some model, right? If you just measure a diffusion coefficient, you get a number. That's all you get, and that's boring. If you try to understand crossover between overdamped and underdamped regimes, what happens at that exceptional point, there's just more physics there where you can try and compare like your idea, whatever model you've got, to the actual to the physics your experimentalist friend is working on. So what I'm going to talk about, I'm going to go through what I think of as a hydrodynamic ideology, a way of looking at dynamics, primarily classical, that's sort of more or less foundational for all of this work. I'm going to talk relatively briefly about two numerical methods. One's fairly old, I don't know, 5-ish years. It's a matrix product operator method. The other is a newish way of looking at operator dynamics, which is what I came and told you all about last year for the people I recognized from last year. I'll talk about long time tails, give a, I don't know, short to medium introduction to what they are. I'll give numerical evidence that they're just not there in the particular correlator we're measuring. I'm not claiming they're not there in general, but they're not there in sort of the natural thing that you measure to measure a diffusion coefficient. And then I'll go talk about this short time oscillation behavior. Okay, so first, this hydrodynamic ideology. The setting is everybody's favorite setting. It's a 1D spin half chain. So here are a couple of examples of Hamiltonians you might want to use. The one on top, let's see, do I have a laser pointer? Yes, I have a laser pointer, is the fruit fly single conserved quantity model that people tend to use, benchmark methods. This one, and this is what I'm going to be talking about when I talk about when I give you numbers and plots. This is from an old paper of Vadim Oganessian, I forget Mukherjee's first name, and David Hughes, where this paper is where I learned most of what I know about long time tails. So that's another good one to have in mind. It has not only a conserved energy density, but also a conserved U1 charge. So to start out with, there's a sense in which this product state I drew is completely correlation free. It's completely disentangled. But there's another sense in which it has lots of correlations, right? So if I write down the density matrix, it has a sigma z on this term, on this site, times a sigma z on that site, times a sigma z on that site, all with high weight. So from a sort of operator expansion point of view, it really makes sense to think about this as a highly correlated state. The dynamics, though, is going to just completely mix all of that long range stuff, right? So you're not going to remember that both spin 2 and spin 127 started out up and were in some sense perfectly classically correlated, right? That's just not relevant. What you're going to see is, after some relatively short mixing time, is a short range correlated state governed by the values of conserved quantities. So roughly what it's going to look like is a maximum entropy state where you have Lagrange multipliers, in this case mu j for the U1 charge and the beta j for the energy density, that get those conserved quantities right. Now, so it's not actually a maximum entropy state, right? It's in fact a zero entropy state, because in this notional experiment I started with a pure state. But the longer range stuff, the stuff that's not maximum, that's not the conserved quantities, it's just random. It's just gotten mixed. It's just gotten mapped to some random nonsense.
How should I understand this in the context of ETH?
So ETH is one way to get here. Yeah. So if I want to think about it ETH wise, the statement is that the off diagonal. So I write my operator in the energy eigenbasis, and the off diagonal stuff defaces. And I'm left with more or less the diagonal stuff, which is which matches the Gibbs state. I don't find that super helpful though. So I find it easier, and I'll talk about this more later, to just say, if you write down the dynamics of, let's say, operators of diameter 6, then that dynamics is chaotic. Like you can measure a gap ratio. You can write down eigenstates or compute eigenstates of that dynamics, and they are hard. So that dynamics is chaotic, and it has some fairly short time scale.
The reason why I was wondering is because I wonder if whether your system has abelian or non-abelian statistics also might matter here. Like Nicole's been arguing that it matters.
Yeah. Oh, so one other point with regards to ETH, even if your system's not ETH, you can still think this way. You've just got a lot more conserved quantities. And this is how you get the generalized Gibbs ensemble, generalized hydro that, like, I think I associate with Serang. I know there are many other people. Mm-hmm. Yeah, I don't know. My intuition is that, again, things that are, so she starts with what? An ensemble that's sort of microcanonical with regard to 2 non-commuting charges. And because it's they're non-commuting, like there's some finite width to those microcanonical ensembles. But when I go to some long wavelength limit, they can get real tight. And my commutation relations, the fact that they anti-commute doesn't matter. So like this picture should still work in some long wavelength limit. Yeah, I don't have a great answer for you, but that's what I've got. While I'm here, other questions from online? Okay. Right. So I'm in this maximum entropy state. The dynamics of my density matrix is, well, it's just given by the Schrödinger equation. But to the extent that my density matrix is fixed by these conserved quantities, I close the dynamics of those conserved quantities. So my charge is just given by a conservation law, but the point is that current is a function of the conserved quantities. I can then do a gradient expansion of that function. Leading order is diffusion. At higher order, I have higher derivatives or higher powers of the conserved quantities. Okay.
I mean, in principle, you have an infinite number of conserved quantities. So what do you mean with conserved quantities here? I mean, any operator is diagonalized the conserved quantity. So
yeah, so I mean local conserved densities.
All right.
And that's a good question. So there's a thing that's going to come back at the very end of the talk where we're going to see something that's basically energy density, that's a lot like energy density squared. Mm-hmm. And I have not all the way figured out how to think about that in this picture. One thing to say is that yes, fine, I keep energy density squared exactly right, but that's some very non-local quantity that I just decide not to care about. Okay. And these you can, in some sense, keep or throw away. You would hope that as you go to longer wavelength, the 17th derivative doesn't matter. Right. So that's broadly where I'm coming from. What I mean by diffusion, why we should. Let's say this. The setup for how to think about diffusion in these cases, numerical methods. Again, probably reasonably familiar. Matrix product operators are good for states with short-range correlations. They're not good for states with complicated long-range correlations. The data you get is a list of tensors. It has the memory requirements for that list of tensors are polynomial in this bond dimension. So as long as your bond dimension is small, that's fine. But if your bond dimension is not small, you're in trouble. Problem is that when you do time evolution, you increase the bond dimension. So you got to come up with something to do. One thing you can do is so-called density matrix truncation. So you do, let's say, a single Trotter time step. You've developed long-range correlations. You need to do a truncation. The way you do that is you write a very specific truncation that exactly keeps 3-site reduced density matrices, does an SVD on the long-range correlations, and keeps large singular values, so large principal components of a long-range correlation matrix. So what you get exactly is the conserved quantities and the conserved currents, or the currents of the conserved quantities, where again I mean the local stuff, charge, energy, density. And then you have some hope that if there's more structure, you'll go find that. And this has turned out to work pretty well for integrable systems, in addition to the chaotic systems that I'm talking about.
But how do you know that you're not tricking yourself?
What do you mean?
Like, how do you know that your SVD decomposition doesn't give you some specious representation of long-range systems?
So, two things, maybe three. One is that as you increase the bond dimension you allow, you, in principle, approach an exact, genuinely keeping the whole dynamics. So, you do a whole sequence of bond dimensions, and when your answers stop changing, you say that's good. Now, that itself is a little specious, right? Because you've got a 100-site system, and so the exact bond dimension, because it's matrix product operator, is 4 to the 50. You're nowhere close. You're like bond dimension 512, but you still say, well, I've done 128, 256, 512. I'm getting the same answer. It's probably right. The other thing you can do is you can check against different methods. So if you can check a relatively small system against Krylov. One of the things I'm going to real briefly talk about is comparing this method to another method, which is not a matrix product operator method. It encodes a lot of the same intuition, but is not an MPO method. So the fact that those give like bang on the same answers is, I suppose, comforting. It's not.
So there's no proof?
No.
Because there are these techniques that people have been working on where there are proofs of how well they work.
For dynamics?
Maybe not for dynamics, but like I was thinking of the Oscillations.
Yeah.
The state information.
So I think of that as like finding the low energy subspace,
right?
Which is like ideally just like the single ground state or the few ground states.
But my point there is that they have a precise understanding of how their overspace truncation affects their error.
Yes.
Rigorous.
Yeah.
And I guess my question is, what is the closest to that you can do in this?
So I don't think there's anything out there that's going to genuinely satisfy you. There's some work of Frank Pullman, Kurt von Kaiserlink, Tupor Rakovsky, where they imagine taking the Heisenberg dynamics and thinking of it in sort of a path integral way, and asking roughly, so suppose I want to think about paths from energy density to energy density, for example. Suppose that path gets out to the diameter 12 operators or whatever. What are the odds of it coming back? And that gives me a handle on the effect of those long operators. So first of all, this is not about DMT. It's motivated by similar intuition, and it's not unrelated, but it's not a statement about DMT. It's a statement about a sort of an abstract thing. Second of all, their calculation was not super rigorous. It was thoughtful in expressing intuition and combinatorial effects. So that's one answer. Another answer is I'm going to again talk very briefly about this operator chaos picture. which is, again, not rigorous, but they're like numerical things you can go check that are not do the dynamics through, like measure something else. Okay, so next up is exactly that, operator size truncated dynamics. This is the part that's familiar or probably not familiar to people who were around last year. The notion is this: let's take everybody's favorite fruit fly Hamiltonian. Start with a single on-site operator, sigma x on the second side. Let's see. Okay. Take the derivative of that. Get that by commuting with the Hamiltonian, and that's the that is the sum of some number of terms. I can think of that as hopping on a graph, right? So this should be a sigma x there. That sigma x is connected to these other guys by links in the graph. I can do the same thing for each of those guys, right? Meaning my graph has it's a whole graph. It's not just those three terms. When I organize, well, I can let me see. If I gather all that up, I can exactly map the Heisenberg dynamics to single particle hopping on this graph. So far, no funny business. It's an exact mapping. I'm not going to say it's completely trivial, but it's pretty trivial. The non-trivial thing, yeah, and I always have to emphasize that this is not Fock space. It's a different graph structure for your many particle dynamics. This gets more interesting when you organize by diameter. So energy density is a sum of, that's the quantity I care about. This is a sum of local operators. So let me just think about the dynamics of this local operator. Derivative of a one-side operator is a two-side operator. Derivative of a two-side operator is a one-side plus a bunch of two-side terms plus a handful of three-side terms, and so on and so forth. So if I organize, let me think in 2 dimensions. There's no reason for me to just do this in 1 dimension, right? If I think in 2 dimensions, I can organize these operators by the size of the bounding box. I can say, well, a string in the size L box, meaning roughly L by L, that has perimeter-wise, if that, connections to smaller operators. It has volume-wise connections to other size L operators, and it has perimeter-wise connections to larger operators. So because my graph separates, so my graph separates in this way. It's tightly intra-connected subgraphs corresponding to operators of similar size that are weakly interconnected. It makes sense to think of my dynamics as those pools connected weakly. Then I recognize, and this is just a thing that you can go check by numerically, that the dynamics restricted to particular sizes is chaotic. So I confess I've only actually checked this for the fruit fly model. But if I do that, I take the diameter 7 subspace, I measure the gap ratio, I deal with whatever symmetry problem. I see that when this integrability breaking term is 0, I'm at the free fermion point, I have Poisson statistics, I'm not chaotic. In the limit of large Z field, I'm perturbing around a different integrable model, namely just a paramagnet. So I also am going to approach some small gap ratio. It's actually going to be set by degeneracies. And in the middle, I have a big old region where I'm chaotic. Gap ratio matches the GOE number. This is not the only thing you can check. I think it's more enlightening to check how spread out your eigenstates are.
How do you find chaos here?
So the thing I care about is actually how spread out the eigenstates are. So if I take an IPR of the eigenstates of this Hamiltonian, I plot gap ratio because it's the thing people always plot when they're asking if something is chaotic. So because because the dynamics of a single pool for a large diameter is chaotic, I can just replace it by some dumb ansatz, like some sort of decay. And we can go talk about what sets the decay rate and so on and so forth. But really, I just replace it by a memory kernel. I can get away with that because the dynamics are chaotic. So this gives me a Stossel ansatz like Boltzmann had. And it also gives me a tractable effective model. So small operators I'm going to treat exactly. Large operators I'm going to treat by this memory kernel. And I say memory kernel, really it's just an exponential. So the whole thing is still linear, but not Hermitian dynamics. Okay. Just to show you how this works. This on the left side here, these are diffusion coefficients extracted from, well, this method, this model for a particular set of hx and hz compared to Krylov. It's off by in the limit of large L star. So when I keep larger and larger operators, it's off by 2-3%. I think that's actually an error in the Krylov. I think that's actually finite size effects because I can only go to 22 site systems on the Krylov. When I compare this method to DMT, the two are again, they're bang on. And if you plot this guy on a log-log plot, it's sort of funny. They line up like wiggle for wiggle. This current correlator, which is what this is, displays roughly an exponential decay, but it's got some oscillation on top of that decay, and we're getting the period of the oscillations, right? So this seems Ning. This is not an answer to the question you asked, but it is a reason that I'm happier to trust both of these methods, right? Different assumptions, similar, related intuition, but different assumptions, and they give really bang on the same answers. Okay, long time tails. So before we get there, I want to talk about diffusion. The setting in which I find it natural to think about diffusion is the following. Let me just quench. So I start with some background. I impose, I drop in a little lump of charge right in the middle. I watch it spread. On long time scales, the width of the region where I have non-trivial charge is going to go up linearly in time. The diffusion coefficient is the coefficient. On short time scales, it's not going to be linear, but I can define some effective time-dependent diffusion coefficient. And this is like purely a convenience, right? It's not a long. It's a thing that approaches the long time diffusion coefficient as I take time long. And if I have a Hydrodyamic model, because for reasons I will get to in just a second, this d of t is going to exponentially approach the long-time diffusion coefficient. There's an identity. This is just a matter of using conservation. So dt of q is grad j, or sorry, div j, and messing around with I think there's an integration by parts. You're using time translation invariance, space translation invariance. You can rewrite this d of t as the integral of the current correlator. So if you want, so the current correlator gives you how that d of t is changing. And if you want to see how your diffusion coefficient is approaching its long time value, then yeah, you can directly measure d of t, but that's a pain. You have to figure out what to subtract off and try and plot that on a log-log scale, on log-log axes, or you can just measure this current correlator. And that's what we're going to do in the numerics later. It's also the right way to get to the long time tails. One sort of funny thing is that if I think about what's going on here, well, the current in this gradient expansion is given by grad of, here I've written it as a number density. I apologize, I should have used Q throughout, which means that the total current is just 0. What that's telling us is that really this integral, the interesting part of this integral happens before this mixing time, right? When you're not, strictly speaking, governed by the hydrodynamics. That's true if you're purely diffusive. If you're not purely diffusive and you add, well, there are many terms you can add. You can keep going up in this gradient expansion. The pure derivatives, so just this, the fourth derivative or the third derivative of charge is a total derivative not going to contribute. These quadratic terms, though, can contribute to a total current. This is a thing you can see just by messing around with the integral. I find it easier to understand this current as each conserved quantity as facilitating the transport of the other. So if I think about the charge transport, I have a region where the transport is facilitated, so it's going to go right real fast. I have a region where the transport is not facilitated, so it's going to go left substantially slow. And this is ultimately how you get out, I think this is the intuition that leads to that non-zero integral. If you do a sort of perturbative calculation, and this is again straight out of that paper of, among other people, David Hughes, you get that the diffusion coefficient is, or the time-dependent diffusion coefficient is going to relax like a power law. I'm sorry, this should be I guess a constant minus that. No. Okay. So we do this. This is DMT, right? So the matrix product operator method, but here are the wiggles that I was talking about. Those are, again, we match the period of those wiggles. The reason this looks sharp is that our Trotter step is fairly large. It's like a half. We can do this integral. We can get some fairly precise estimate of the diffusion coefficient. The uncertainty comes from a couple of things. One is that this convergence is pretty good, but it's not perfect. So 256 and 512 are differing down towards the end of our simulations. And the other is that this is not the only correlator that you can measure, right? You can measure an energy correlator and you get like 1.4, I think you get like 1.45. So you differ in this last decimal place. We have not nailed down why that is. I think that is well within the precision of anything that we would hope to measure in an experiment or anything. So this does not worry me. That's a problem for down the road. Okay, the other thing to note is that really, we have 3 decades of exponential decay in this current correlator. There are not long time tails showing up in this guy. If you count the things that are faster than exponential, we have 5 decades. I do not think it's there. Now, the question is why. I thought I had an explanation. I was talking to Braden, my co-author, last night, and we realized that actually there's one piece of this that's missing. If I think about sticking a gradient expansion for the current into this spatial integral to get the integrated total current, the name of the game is to look at each term and show that it's a spatial derivative. These pure derivative terms are obviously total derivatives. They disappear. These guys, you can play some integration by parts games and recognize that they disappear. That these folks already understood. There's a cryptic line in their paper that works out to this. We could not figure out these guys, which again, there's a cryptic line in this paper suggesting that these guys are the place you would see long time tails. Sure looks like there's some symmetry reason why this should be 0 at all orders. again, fairly long times, good convergence in our method parameter. Two different methods. I'm only showing one here, but we have two different methods that give really almost exactly the same diffusion coefficient and the same correlator. Looks like it's not there, but we don't know why. So if there's some obvious reason that we're missing, please come bug me, send me an email, something.
So let me clarify.
Yeah.
So this is ambient temperature,
Yes,
and what's the system size?
this is 100 sites,
100 sites.
but the lump in the middle has not spread to reach the edges.
Okay, that's the question then.
Yeah.
And the other one is you're still truncating the correlators, so the density matrix. I mean, I actually don't know exactly how you do that, but you're keeping only like finite length correlations, right? Like,
So we guarantee the finite length, the short correlations. We guarantee the 3 site density operators.
right.
We don't guarantee the long range stuff, but for the long range stuff, it's morally like TV. You do an SVD and you keep the big singular values, and those aren't what they are.
All right.
Are you saying that there's like what would be different if you saw long-term tails here?
Oh, this would look straight on a log-log plot, not a semi-log plot.
Okay.
And so I didn't put it in, but it's just you can plot this on a log-log plot, and it's curved. It's just like really obviously curved. So I don't know, like the field theory people, or the people that write down these Schwinger-Keldysh effective field theories for hydrodynamics, it's surprisingly hard to pin down from reading their papers, but they seem to think that there should be long time tails. There's no reason that we can think of that you wouldn't see that term, but again, you go do the numerics and it doesn't seem to be there. Maybe there's another correlator that would display long time tails, but like this is the correlator we care about, right? We care about transport. We want to know diffusion coefficients and conductivities. Doesn't seem to be there.
Can you construct? What would it mean if you had a theory for which certain correlators had long time tails and certain correlators did not? Like, I wonder if there's some sort of argument that you can make that if you don't see long time tails in some class of correlators, it's sufficient to demonstrate that it doesn't appear.
I'm sorry, I'm not quite following. Can you?
Well, I'm just trying to figure out what the necessary and sufficient conditions are for demonstrating that no correlator in your theory can have long time tails. Like, so if I demonstrate these 8 correlators all don't have long time tails, is that sufficient to demonstrate the rest of them? As long as I pick the right correlators.
Yeah, I do not know. That's a very reasonable question, and I don't know.
It seems like kind of bizarre physically to have a theory where some correlators see it and some correlators don't. You would have to have a physics reason.
Yeah, I agree. One, you're probably not going to be happy with this as an example, but if I think about charge versus current, charge is going to decay like a power law, right? 1/10⁻². Currents, nothing stopping it from decaying exponentially, right? Now, you probably don't want to think of that as a long time tail since that's the leading order in the expansion, but it is an example where one quantity can have power law decay and another doesn't. And that comes, so well, maybe more things to say about that. Yeah, I don't have a good way of thinking about this.
What if you have U1 symmetry? What do you see? Have you tried that?
We are getting the U1 code up and running now. So in this paper they did U1 and they saw long time tails. Now it was Krylov, so they looked at a frequency dependent conductivity and they saw like less than a decade, I think, that matched up with their predicted exponent, because it's super small systems, right? Yeah, so my expectation is that we'll see the long time tails. If we don't, then that suggests the methods are bad. All right. Okay, before I move on, I want to mention that Stuart Thomas is the guy that did all of the actual work here. Well, he did the majority of it. Braden Ware also did a substantial fraction. Stuart has been a joy to work with, and like, I don't know, if you get the chance to hire him, you should hire him. He's not on the market. He's fairly young, so he won't be soon, but he's great. Right. So this is just what I was saying earlier. There are a number of terms we understand. This last term we do not. Okay, short time oscillations. We're motivated by an experiment. This is, I think it was rubidium in an optical lattice. You cannot see the names you would recognize, but those names are Wasim Baker and David Hughes. They take a 2D optical lattice. They set up density oscillations. They watch them relax, and if you just naively think about diffusion, you would expect that would just decay like an exponential. They don't see that for short enough wavelength, and these different curves are, I think, decreasing wavelength. They see oscillations. Then this figure is straight out of their paper. They have, there are two pieces of an explanation. One is that in the starting configuration, the time derivative of the number density on each site is 0. So because the state you prepared had no current operator. So there's something else going on beyond diffusion at these timescales, and you can see that behavior in the beginning there. The other thing is that if you think about this effective theory, well, I spent a bunch of time talking about a gradient expansion in momentum, but there's no reason you shouldn't also do a gradient expansion in time if you want to get beyond the lowest frequency behavior. And this is exactly how, this is not a contribution of mine, this is exactly how they analyze this. I think these curves are fits to this prediction. So that's all reasonable. The question is like where this comes from microscopically, and if there's some story you can tell that explains how this comes about. One story you can tell is you can take a Hubbard model, you can add long-range interactions in a way that minimizes the decay of the current. And you can see that the result is that the current doesn't decay, so you have oscillations along these lines. I don't know, I am curious about the logic behind that paper, because it seems like, yes, in some sense it's motivated by this experiment, but it also seems like the sort of construction that's interesting for other reasons, just a weird, interesting thing. I don't think that construction is why this oscillatory behavior shows up in Wasim Baker's experiment. I think that is just a generic feature, and I'll say why in a second. I think this hot band sound business with the minimized scattering is like, again, I'm curious about Vera Bolchandani and David Hughes's many other reasons for writing down that model. It seems interesting. Right. So in our fruit fly model, we can do some similar thing. We don't actually prepare Fourier modes and watch them decay. We instead put a lump of energy density in the middle, watch it spread out, and just take an FFT, right? But because it's it's a large system, we have not hit the edges. We can think of that as probing the decay of Fourier coefficients to the extent that our dynamics is linear, which we're sort of now working on that assumption. And we see exactly the same oscillations. Maybe not exactly. So the solid lines are data from our MPO method. The dashed lines are fits to a simple harmonic oscillator ansatz that I'll talk about in a second. It's not perfect, but it's pretty good. So we're seeing the same behavior in just the first model we tried. Now, maybe this fruit fly model is special. You know, people use it because it's extra special. It's, you know, very ETH. That's another thing that was a paper of David's from a while ago. Maybe there's something special about that model that prevents scattering, but I don't think so. I think this is just a generic thing. Before I talk about the microscopics, this is a plot of decay rates, which here we're calling VerPi, extracted from, actually, this is a slightly different fit. It's also an exponential fit. I do not remember the details of this. For long wavelengths, so short, small wave vector, the real part of the decay rate, which is, the real part of VerPi, which is a decay rate, is cleanly parabolic, agrees with the diffusion coefficients we saw in all of these other ways. The oscillatory part is 0, goes through an exceptional point where the eigenvalues, the decay rates develop imaginary parts, and you start seeing oscillations. So this is just a few momenta. This is what it looks like across momenta. So I think where this comes from is understandable via the Liouvillean graph operator size truncated dynamics picture I was talking about before. So just to remind you, the story is I rewrite my Heisenberg dynamics as single particle hopping on a graph. If I use as my initial operator a Fourier mode of energy density, well, okay, so that is going to connect to a Fourier mode of the energy density current, which is then going to connect to other operators. In the same way I thought of these long operators as chaotic, I can, at the level of a toy model, I don't want to claim that this gets the details of the physics right, but at the level of a toy model, I can just replace all of this by a decay gamma. And when I do that, well, okay, so this becomes a coupling to the current. The current couples back to the energy density. I add in this artificial decay to mock up these other operators, and that's just again a toy model. And I want to emphasize that this is exactly the ansatz that the folks used in analyzing Wasim-Baker's experiment. The difference here is just that we have a microscopic picture behind that sort of long wavelength gradient expansion logic. And again, because we have this microscopic picture, this is what makes me say it's generic, right? There's nothing that would prevent this same microscopic picture from working for, pick your favorite model. When we compare just pulling, well, I guess there are two fit parameters. There's this gamma, and then there's actually a hopping coefficient, call it a T, that comes from a norm that we could in principle calculate, but we don't. We just leave it as a fit parameter. Two fit parameters, we get these dotted lines out of the toy model, and they display qualitatively the same dynamics. Again, I really, really want to emphasize that I don't claim that we're getting the dynamics exactly right. I want to claim that this is a toy model that explains the microscopic origin of the oscillatory behavior. That's great. That's cool. Life seems like it's making sense until you go actually look at the spectral function that you can pull out of this operator size truncated dynamics. Your first thought is that this looks great. There's a slow, so what I'm plotting is momentum and then the real part of the decay rate. So there are no oscillations here, and I'm sort of integrating across the imaginary part. So this is maybe not as informative a plot as you would hope for it to be, but it is informative in its way. I've got a slow mode. If I just plot dk squared with that diffusion coefficient that I got from all kinds of methods at all kinds of different parameters, lines up perfectly out to some, looks like kind of like an avoided crossing. There's bunch of noise up there. My bet is that that's going to turn into a continuous band as we increase the size of the operators that we keep exactly. And you even start to say, well, maybe this avoided crossing matches up with that exceptional point. But then you actually look at the numbers and say, well, I was dumb because we made these plots at a year apart, and this exceptional point maps to what 0.15 pi would be like over here. So like quantitatively doesn't really match up. The other thing, then you ask further questions. This, I didn't plot it, but this is constant plus d squared. The other eigenvalue here bends down. It's constant minus dk squared. And then if you just look at the operator content of this mode, that's some mode, right? Corresponds to some eigenvector of my effective dynamics. I can just print out what the states are. It looks like energy density squared. So this is probably like the restriction of energy density squared to this diameter L star. And the other mode in this toy model is some nonsense up here, hidden by that band, that comes down and meets in an exceptional point at some more reasonable k. If it's there, if I'm right about this toy model, right? This toy model is, I find it very intuitively plausible. It explains some things, but I don't know. I don't fully understand this story. So I want to be very explicit. There are things about this picture that do not add up. And, so probably what we're going to do is we're going to publish it as a methods comparison paper, which was the original goal, and continue thinking about it. But I think this is really interesting. It seems like, there's just some there's some question that we don't understand here. So to wrap up, I explained a couple of methods, this matrix product operator method, the operator size truncated dynamics. I said we can get to, well, I think of it as high precision. I'm not sure Adrian would agree that 1 part in 10 to the 5 is high precision, but I think of that as high precision. The two methods agree pretty well. We've reproduced this oscillatory behavior in just, the fruit fly model with the fruit fly parameters. We haven't twiddled the knobs, but it seems to be there. And we came up with a microscopic toy model that is motivated by this method and reproduces the oscillatory behavior. Where this is going, well, in 1D, U1, we need to do U1. That's next on our list. I'm talking to somebody about doing power law hopping, which, I don't know quite what's going to happen. Whether we should think of that as a methods paper, as hydrodynamics. I don't know what's going to happen there. I'm excited to think about finite temperature. So I'm curious about temperatures of order gap in some system. So 2D, this is I think possible but non-trivial. I don't know, been talking to somebody about trying to do cylinder DMT, right? So just map these MPS or do these MPS methods on a cylinder. You can combine DMT with ISO-TNS. I actually have code for that, but ISO-TNS is hard. I ran into some numerical instability problem that I never got past. I spent, a couple months over December, January working on this and just didn't get there. With the operator size truncation, I think if we had a better memory kernel, we could do 2D. The problem there is that like you do 3x3 bounding boxes, you do 4x4 bounding boxes, you're converged to like within 10 or 20%, right? You can't do 5x5. And so if we had a better memory kernel, maybe we could get like 3x3 and 4x4 to match up. But you got to be really sure that memory kernel is right for like other reasons, because you're not really checking convergence, right? So that's non-trivial. 3D is never going to happen. We can talk about why. I don't think we're going to do 3D. I don't think we're certainly not going to do non-trivial gauge theories in 3D on classical computers. I think they're fun things to think about as far as digital quantum simulation. So in the far future, you're going to be limited by non-Clifford operations. What can you use the things we understand about hydro to reduce your costly operations? And before the far future, can we get away with like limited error correction using error correction for error mitigation, or the tricks we can pull? So that's something I've started thinking about. I don't know, that's not going to be useful for 10 or 15 or 20 or 30 or 40 years. But it's fun to think about. Okay, other questions?
Just a suggestion.
Yeah.
You said that you use a very large trotter step.
Yeah.
Probably things won't change qualitatively if you make it smaller, but quantitatively they might. I just wonder. I mean, I think it might be
So
I mean, good idea to just compare to convergence with the trotter step.
we did. And it's convergent trotter step. So
Oh.
this is a fourth order trotter step with step 0.5.
Or fourth order. All right.
Yeah.
Okay.
And then if you go down to like 0.3, I think we did 0.6, 0.5, 0.4, 0.3. 0.6 is different, but 5, 4, 3 are all the same. And because it's fourth order, sort of expect that it would. It's not so crazy. The trotter step of a half. Would work. And like I said, it seems to be converged.
So I'm speaking without the knowledge of the subject, but this operator tree that you built.
Yeah.
Right. You told us a story last year. I'm just trying to remember exactly how it works, but there is an idea by Auerbach and Altman where they did something similar, I believe, when they were studying scrambling.
Is this the universal operator growth hypothesis? Dan Parker, Ehud Altman from like 2019?
Yeah. Maybe.
Yeah.
Yeah.
So that actually, we tried that. That gives bad diffusion coefficients. It just doesn't work.
Mhm.
And actually, so if you look at, I again didn't show these plots, but if you look at this, where is it? Do I have it? I thought I had it. If you look at the current correlator here, that differs just real early. So what's going on is it gets the dynamics right as far as you have exactly computed the Krylov coefficients.
Mhm.
But as soon as you start using this hypothesis,
Right.
it's just wrong.
I see.
Yeah. So, we don't understand in detail why, but like that ansatz is just not capturing all the physics you need to get the diffusion coefficient right.
All right. Good to know. All right. Do we have any questions from the online audience? Please feel free to unmute yourself and ask. All right. If not, we thank Chris one more time. First time. We thank you. All right. Thank you, Chris, for nice talk.